In the last lesson, I showed how easy it is to make your programs go horribly wrong just by reading some strings entered by a user, which ended up corrupting some memory. In this lesson, I'm going to explain exactly what that memory corruption really is and how it happened. We'll be looking at quite a bit of technical stuff in this lesson, at memory and addresses, buffers and buffer overflows, the stack and stack corruption. By the end of this lesson, you will understand a lot of stuff that most programmers never really do. I'm Hugh, and this is a lesson in my course on programming C in Visual Studio. In the last lesson, I showed a problem that occurs when I read into strings called first name and last name. Here, first name and last name are arrays of characters, and that's how we create strings in C. Some of the characters from last name flowed over the end of that array, and those characters ended up writing over some of the characters in the first name array. That's because my character arrays, first name and last name, have each been declared to hold 8 characters maximum, but my surname happens to have 13 characters. So when I enter my surname, the extra characters flow over the end of the last name array. But the mystery is, why did those overflowing characters overwrite part of the first name array? After all, first name was both declared and initialized before last name. So you might have expected the characters of first name to be lower down in memory than the characters of last name, in which case any extra characters at the end of last name should get written somewhere even higher up in memory, so that the first name array, which is lower in memory, should not have been overwritten. But that's not what happened. And to understand why, you need to know a bit about the stack. When our programs use data, that data is generally stored in one of 3 memory areas. First, there's an area of memory reserved for global data, which includes things such as string literals. Then there's the heap, and the heap is where data for which memory was allocated using functions such as malloc and calloc is stored. And finally, there's the stack, which is where local variables, that is, variables declared inside functions, that's where they are stored. In this program, my character arrays are local to the main function, so they will go onto the stack. Every time you call a function, a chunk of memory called a stack frame is set aside to store the state of that executing function. So if function X calls function Y and function Y then calls function Z, there'll be 3 stack frames, one on top of the other. In the stack, there's X, then Y, then Z. When function Z exits, its stack frame is removed, leaving just X and Y, the state of those functions, on the stack. And the same is true when you call a function recursively. If function X calls itself and then calls itself again, then for each function call, a stack frame will be put onto the stack. In fact, I've got a different video explaining recursion, and the link to that is under this video. In the program I've been running, I can see that just like the stack frames, the local variables also grow downwards, by which I mean each variable I declare is stored at a lower address in memory than the one I declared before it. I've shown the addresses here of 4 integers and 2 character arrays declared in this order. Look at the addresses. Each one is lower than the one above it. So the variables are growing downward in memory, but an array grows upwards. Look, I can show that here by printing the address of array offsets. The address of the character index 0 is the same as the address of the array itself. The address of the character at index 1 is 1 byte higher than the address of the array. The address of the character at index 8 is 8 bytes higher. 8 bytes higher than the address of the last name array. Oops, that's a problem. Because that's the same as the address of the first name array. Look, that's what this shows me. And that's why when I enter characters that flow over the end of the 8-character last name array, they start to overwrite the characters in the first name array. The addresses of characters I'm trying to put into last name are now the same as the addresses of characters which I've already put into first name. This is because the address of the last name array is lower than the address of the first name array. But remember, the array itself grows upwards. So the address of each element is higher than the address of the preceding array element. As the last name array grows upwards, it eventually spills over into the memory being used by the first name array. And that's when the corruption occurs. And it's why the characters in the first name array end up being overwritten. When the characters spill over the end of an array like this, we usually call it a buffer overflow, which is kind of confusing because buffer is normally a word that we use to describe a temporary storage area. For example, the keyboard buffer, which stores characters entered at the keyboard until your program has the chance to read them in and use them. My character array variables here are not intended to be used in that way, as temporary storage, I mean. So strictly speaking, they're not buffers. It would be more accurate to describe the problems I'm having as array overflows. The confusion of terminology arises because buffers are usually arrays, and buffer overflows are, in essence, the same as array overflows. So the term buffer overflow has stuck. Incidentally, when overflows like this occur, they can cause far more serious problems than I've encountered in my program. That's because it's not only the variables inside the executing function that grow downwards in memory, it's also the function calls. Remember I said a chunk of memory called the stack frame is created to store the internal state of each function call. So if function X calls function Y, then the internal state of Y is stored lower in memory than the internal state of X. But if an array in function Y suffers from a buffer overflow, that is, if you try to add more elements to the array than it's capable of holding, that data grows upwards in memory, and it might eventually spill over into the stack frame of the previous function, function X. So when function Y exits and your program goes back to running the code of function X, the internal state of function X might have been corrupted, and your program could go completely and horribly wrong, and you'll end up with a bug that might be extremely hard to find and fix. Incidentally, stack frame corruption is a tried and tested way for hackers to gain control of a program. So anything that has even the remote possibility of this occurring is definitely something you need to avoid. One final thing is worth mentioning here. While stack frames, the memory set aside for each function call, invariably grow downwards, the order of the variables declared inside a function is not a guarantee of their ultimate locations in memory. In my examples, I showed that the variables do grow downwards because each variable's address is lower than the address of the variable declared before it. But that might not always be the case. Now let me run this program in the debug configuration. And when I run it, I notice first of all that these integer variables up here, whose addresses I've displayed here, they all have lower addresses. Each subsequent variable has a lower address than the one that went before it, the one that was declared before it, as you can see in the code. And the last name address here, the address of the last name array, is also lower in memory than the first name array, as I can see here, 3.6 versus 4.4. But the array itself grows upwards, as I can see from the addresses of the array offsets, with each one having a higher address than the one that went before. And in fact, you can see at the address of the last element, that's at array index 8, it overflows into the first name array because this address is the same as the address of the first name array. So that explains our buffer overflow, but this isn't necessarily always the case. But now let me run it in the release configuration. And I run it again. And once again, I can examine the addresses of the variables and the arrays. Well, the addresses of the 4 integers continue to grow downwards, 24, 20, 16, 12. But the address of the last name array, here, well, that's higher than the address of the first name array. So as I mentioned previously, debug and release configurations generate different code. The debug configuration may pad out memory by adding characters to mop up buffer overflows. The release configuration may optimize your code, and that could include reordering the addresses of variables or arrays. The arrays themselves, the elements in the arrays, continue to grow up, and I can see that from the addresses of the array offsets. Each address is 1 byte higher than the one that went before it. But now the last name index 8 does not overwrite the first name array because its address is higher than that array. And that explains why when I compile this program for release, I don't see the same error as when I compile it for debug. Let me show you here. Enter my name and all appears to be well. The last name array has a higher address than first name, so the overflowing characters don't write themselves into the first name array. But even if the obvious problem doesn't show up right away when I compile for release, that does not mean that the bug has gone away. It just means it's harder to spot. Those additional characters, the ones that extend beyond the 8-character array which I declared for last name, still end up in memory that hasn't been set aside for them. So they still risk writing over memory that's used, or that later on in the program will be used to store some other data. They could even extend far enough up in memory to overwrite the previous stack frames. That's the memory set aside for the previous function call. And that is definitely a very, very bad thing. Okay, so we've come a long way over the last few lessons. This all came about because I wanted to show you just how bad the scanf function is, and how easily it, and also the getS function, can corrupt your programs. But if scanf and getS are so bad, what better alternatives are there? Well, I'll have some suggestions in the next lesson. Thanks for watching. To be notified whenever I upload new lessons, subscribe to my channel and click the bell. To follow this course in order, bookmark the playlist which is shown under this video.